Okay, guys. So during our last lecture, we started discussing Aldol reactions. And we specifically discussed the fact that this is between two carbonyl compounds, typically aldehydes or ketones. I introduced two aldehydes and two different aldehydes. They don't have to be, but they can. The reaction is catalyzed by a Lewis acid, typically a boron Lewis acid, in the presence of an amine base, whether it's triethylamine or dipea, to give you a beta hydroxy carbonyl compound. We talked about the two stereocenters that we form that we typically don't discuss in Chem 124, and that because we have two stereocenters, we have four possible products. And we talked about all those four possible products where the end goal is really to just form one out of the four. And what we were going to do is start off slowly and just focus on forming two out of the four. Okay. And so we discussed the Lewis acid. And we talked about the fact that when R is a small group, and I gave you a number of examples of these types of R groups, the reaction favors the formation of the Z-enolate. When R is large, the reaction favors the formation of the E-enolate. Okay, and so let me draw that out for you. And again, this is just from our previous lecture. And a quick review. So there's our Z and our E-enolate. Now, when you introduce a carbonyl compound as your electrophile, the Z-enolate will always give you the two syn products. And by the two syn products, I mean the wedged syn products and the dashed syn products. Whereas the E-enolate, in the presence of your carbonyl compound, will give you the anti-products. And both anti-products and so let me draw these out for you. And so there are our four possible products. Now, in our previous lecture, we just focused on why we were forming the syn products from the Z-enolate. We drew out the six-member transition state, the Zimmermann-Trexler transition state. I drew it for you three-dimensionally, and then I unraveled it and drew it two-dimensionally with wedges and dashes. And that's where we stopped. And we were able to explain why we see both products and specifically why we see the syn products. Now we're going to discuss the E-enolate and why the E-enolate gives us the anti-products. So why does the E-enolate give the anti-products? And the beauty of it is that it also proceeds through a Zimmermann-Trexler six-membered ring transition state. So this is really great practice for you to get used to drawing chair conformations, drawing them obviously three-dimensionally, and then unraveling them and then redrawing them two-dimensionally when you've proceeded through your reaction. So let's go ahead and start off here. I'll go ahead and continue to draw my E-enolate and my carbonyl compound, two different colors. Draw out my E-enolate in red to try to stay consistent. And my carbonyl compound in blue or purple maybe. And again, you get two products. So we'll discuss both products just like we did before. So remember, our carbonyl compound is approaching our enolate, and the carbonyl compound can approach from the front and the back. It doesn't have a preference. It's not front or back, it's front and back. And because it can approach from the front and the back, you get two anti-products. That's the rationale. Now, what we're going to take a look at is the carbonyl compound approaching the E-enolate from the front. And so we're just going to focus on the carbonyl compound approaching the enolate from the front, and we're going to do the exact same thing that we did before. I'm just going to redraw my E-enolate. And just like before, I rotated it to the right slightly, about 90 degrees, and I'll draw it in red. Now, what I want you to notice is that the way I drew this enolate, this is my E-enolate. In last week's lecture, my ARG1 group was facing down. Now it's facing to the left, right? Because it's my E-enolate. Okay? Just like before, in our previous lecture, our aldehyde approaches from the front. And if you remember, it has to approach a very specific way, and I'll redraw this in blue. And if you remember, I also was trying to redraw my two molecules in a way that I can see the six-membered ring transition state that I'm forming. And so I can draw the hydrogen facing up with our two group facing away. And if you remember, I specifically said that the hydrogen group can be facing up or it can be facing the other direction. So let's draw that as well. I'm going to redraw my E-enolate over here. Just like we did before. Redraw my carbonyl compound approaching from the front. But in this case, with my alkyl group facing up in the axial position and the hydrogen facing towards the left. And again, we did the exact same thing for the previous lecture, and we talked about this transition state. And so we started drawing arrows to show the flow of electron. The carbonyl oxygen complexes to the boron, regenerate my double bond, and attacks my carbonyl. And you can kind of start seeing the six-membered ring that you're forming. And because the reaction is proceeding via a six-membered ring, the transition state has to follow the rules of a six-membered ring conformation, where you don't want diaxial interactions. And so you can see in this case, to the right, because I have an alkyl group that's pretty bulky, I have diaxial interactions with the other substituents that are also facing the top and are axial. In this case over here, it's a hydrogen that's axial. It's a lot smaller, and despite the fact that it also sees 1,3 diaxial interactions, they're not as excessive as they are in this example. So this is not the transition state that is favored. Again, very similar to what we saw in our previous lecture. The only difference is this R1 group. That's it. Because it's the E-enolate as opposed to the Z-enolate. Same rationale. So because it is the same rationale, this is really great practice for you to draw six-membered rings. So this is, our favored transition state. And just like before, I am going to redraw it and maintain it in its chair conformation. And I want to maintain it in its chair conformation because it's easier for me to see it that way. If you can see it in two-dimensional form, by all means, whatever works for you, as long as the stereochemistry is correct. Let me draw the rest. My hydrogen is facing up. It is now an oxygen-carbon single bond. My oxygen is now bonded to my boron. So there's my final product, or not my final product, but my product from my Zimmermann-Trexler transition state. You can protonate this with a proton source, whether it's acid or water, right? And if we redry it again, it looks exactly the same, but now it's protonated. So let me go ahead and do that. And I think it's good practice if you keep redrawing it. Chair conformations can be really hard to draw. So there's my final product. Now what I did before is I unraveled it and I extended it. And just like before, I number this 1 through 3, exactly like before. I like to see it from the left side and the top. So that's supposed to be an I. I'm looking down on it, and I can start unraveling it and numbering it from left to right. Got my carbonyl, which is 1. On my left side, it goes down to carbon 2. It doesn't have to look pretty. You can straighten out the bonds later on. Got 2. Notice that my R prime is facing towards me and poking me in the eye, which means it is wedged. I then go to carbon 3. It's facing up. The hydrogen and R1 are on the same face, so it must also be wedged. Please notice that the hydroxy group is on the complete opposite side of my eye, so it must be dashed, and I can add in the remaining group. Okay. Let me draw this in blue. It may help a little bit more. But what I want you to note is that my R1 and my alcohol are anti to each other. And so that explains the formation of the anti-product, drawing the exact same transition state, doing exactly the same thing I did in my previous lecture, which is really nice. So again, if this is the product that I get from the aldehyde approaching the front of the E-enolate, not surprisingly, when the aldehyde approaches the back of the E-enolate, I'm going to get the other anti-product. So let's draw that as well, just for practice. Vinyl compound approaching E-enolate from back. I'll highlight this too. And I'll continue to color code everything. Again, this is our E-enolate. And our carbonyl compound color coded. I'll draw out my E-enolate first. So there's my E-enolate. Now I'm going to go ahead and draw my carbonyl compound approaching from the back. Remember, just like before, you want, oh, I want this in blue. You want your hydrogen on your carbonyl compound to face the top to avoid any 1,3 diaxial interactions. And then, of course, the rest is to the left, just like before. My carbonyl complex is to my boron, generates the double bond, and the alpha carbon attacks the carbonyl to form what looks like a six-membered ring. Drawing aldehydes coming from the back is a little harder for me. It might be a little bit easier for you, but remember, your aldehyde's coming from the back. I can go ahead and draw the product in my chair conformation, and I'll continue to color code. I like to draw the front first, completely up to you. Okay. Now, if you remember from our previous lecture, again, I like to see it from the top left and look down on it. And if I'm looking down on it, now my carbonyl compound is on the right side. So there's a lot of flipping around. And so if I have to redraw this, let me just protonate the oxygen with acid or water. So all I'm going to do is redraw this, but now with an OH group, as opposed to it being complexed to the boron. Oh, that looks a little messy. Okay. So now I've got my final product. I'll do the same thing. I'm looking at this from the left. And now the way I'm going to redraw it is with my carbonyl group on the right side, carbon 1. There's that. It's going down, so I'm going to go down, carbon 2. Notice that the R1 is facing towards me, so it must be wedged, which means that my hydrogen is dashed. It's now going up, carbon 3. Please notice that my OH group is on the complete opposite side, which means that my OH must be dashed. Let me draw this in blue. And my hydrogen must be wedged because it's on the same face as my R1. And then the rest is the remaining CH2R2 group. Okay. If I flip this 180 degrees so that my hydrogen is now on the left side, excuse me, my carbonyl is now on the left side, then my R1 group is dashed and my OH group is wedged. And now I've got the other anti-product. So I get both anti-products in a 1-to-1 ratio, which is what we covered in last week's lecture. It's a diastereoselective reaction, not an enantioselective reaction because it's giving us two products. And what I want you to note, if you haven't noticed already, or maybe you have, and it's probably a question that's been lingering, this group in our chair conformations. This group really is just trying to avoid being axial, right? That group, whatever Zimmermann-Trexler transition state you've been drawing, has been trying to avoid being axial in order to avoid 1,3 diaxial interactions, which is perfectly fine. But what I want to say is that when I draw it out, if you notice, I don't really care how I draw it because it's not a stereocenter. Regardless of how I draw it, it doesn't matter. It can rotate. It's never going to matter because it's not a stereocenter, so I can draw it any which way. What I care about is, of course, those two stereocenters. Okay? So now we have an idea of why we get syn products from Z enolates and anti-products from E enolates. Let's just do a few examples of this. Highlight this. And we'll do a few problems. Let's try ketones. Okay. And we'll have to fill in the blanks, just like what we've been doing in our practice problems and in our quiz. Okay. So if you remember, first thing is forming our enolate. And in order to draw our enolate, we need to figure out which one is favored. Butyl are small groups, so it is going to favor the formation of our Z enolate. So let's go ahead and draw that out first. So there's our Z enolate. Okay. The two priority substituents are on the same face or cis to each other. Now I take this Z-enolate and I treat it with my aldehyde. I'm going to get two products, and they are going to be syn. And the two products are, of course, the dash products, the dash product, excuse me, there's only one dash product, and the wedged product. And again, you get it in a 1-to-1 ratio, right? It's a racemic mixture. They're enantiomers of each other. We can use the exact same starting materials. So that's what we'll do now. And use a bulkier group on my boron. Continue to use dipea. And again, we need to figure out our enolate first. If you remember, CY just means a cyclohexyl group, which I told you are pretty bulky and favors the formation of our E-enolate. Where the groups are anti to each other, or the priority groups are anti to each other. Once you treat it with your aldehyde, again, you get two products. In this case, anti. So please notice that really nothing has changed from the very general example that I gave you. Let me draw the other anti-product down here. It's all dependent on my substituents, on my Lewis acid. And just like before, you get these in a 1-to-1 ratio. They're enantiomers of each other because they've completely inverted stereocenters. And so we've been able to narrow down our options. We've been able to rationalize why we get two products out of the four. So now we really have to answer the question of how do you get an enantioselective aldol, i.e., how do we get one chiral product out of the four possible? And luckily for us, we use Evans oxazolidinones. Evans oxazolidinones comes back into play, which is really great. You can see how the methodology from alpha alkylation was extended to aldol reactions as well. We won't discuss Andy Myers. We won't discuss SAMP and RAMP anymore. We'll only focus on these oxazolidinones and apply them to aldol reactions. And so in our next lecture, we'll start introducing these chiral molecules again.